Heisenberg's uncertainty principle is a mathematical relation between two variables of a particle. It states that there's an uncertainty to the amount of possible values of these variables while being measured. We'll be looking at the values of position and momentum, but remember that this principle applies to any complementarity variable pairs. All you need to know about Planck's constant is that it's an unbelievably small value, like pick up a grain of sand and throw it away because our brains can't comprehend something that small, and Planck's constant really isn't even a length. Let's look at the single slit experiment. A laser is going through a slit, and you can adjust the slit to make it thinner or wider. As you narrow the slit, the spot on the board also becomes very narrow until, whoa, it became wider all of a sudden. What happened? Well, we can think of Heisenberg's uncertainty principle more as a rule. You cannot break this rule or you break quantum mechanics. The rule says the product of momentum and position must be larger than or equal to Planck's constant over 2. Now, as you narrow the slit, what were you doing? You were making the position of the particle more and more certain by decreasing the possible values. Otherwise meaning that you're making us closer to making our rule untrue. To stop that from happening, the possible values of momentum have to keep going up to compensate. This keeps happening until you notice this full effect. That's how the math works, but what's actually happening? Well, to understand that, we'll have to look at wave-particle duality. We know that particles such as the photons that make up the laser act both as a wave and a particle under different circumstances. Let's play a little game. If I show you this rubber duck, can you tell me where it's located? That's not a really good question because these are all valid positions. In quantum mechanics, it's slightly different. There's never the single position, but a probability that a particle will show up. Let's look at a wave that continues on to infinity. Can you tell me where this wave is? There's no possible way to tell me where this wave is, right? The way we relate a wave and a particle is through the amplitude of the wave. There's a certain probability that a particle will show up in a certain spot, and this is determined using the square of the amplitude of the wave, meaning the larger the amplitude of the wave, the more likely a particle will show up. This is why we're uncertain to where the particle is, but one thing we do know is the particle's momentum. Momentum equals mass times velocity, and using the frequency of the wave, we can determine its velocity. Here's a graph of a particle with a definite location. If we stretch the amplitude of a probability wave long enough, we get to a point where both of these look alike. Theoretically, our probability wave now has a definite position, but now we don't have a discernible frequency. So how do we get a wave with a more certain location and a more certain momentum? Well, we'll use a wave packet, a wave that does not extend to infinity, but a burst of a wave with a definite position. To create this, we'll use Fourier synthesis and essentially place many waves on top of each other. There are areas where these varying amplitudes of these different waves line up, creating taller and taller amplitudes, and areas where these amplitudes meet the value, creating areas of nothing. If we keep doing this long enough, we get a wave that's also kind of like a particle. This is a quantum object. Great, does that mean we now know the exact location and momentum of this quantum object? No. To create this wave packet, we had to superposition many waves with varying momentums on top of each other, meaning any of these momentums could be valid. And to create more certain momentum, we have to remove these waves, creating uncertainty in position.